Good evening, everybody. Today we have an eminent speaker for this Plenty 20 series. Today we have Dr. Asraff, former Associate Director R&D from VSSC, and he is going to give a talk. Now, coming to Dr. Asraff, he did his BTech from NSS College of Engineering, Palkad, and secured third rank, followed by his ME in Structural Engineering from PSG College of Technology, securing first rank. Subsequently, he pursued his PhD in Civil Engineering from College of Engineering, Trivandrum, and he submitted the thesis within the minimum required period of 3 years. He joined as scientific officer in the Nuclear Power Corporation, Department of Atomic Energy, Bombay, during 1989-90 period, and then he joined as an engineer in the liquid propulsion systems in the Valimala, and he served there in LPLC Valimala during the period of March 1990 to January 2020. And subsequently, he took over charge as the Deputy Director of the Mechanical Design and Analysis NDT, LPSC, in February 2020, and later moved on to VSSC as the Deputy Director of the Structural Engineering NDT, and superannuated as Associate Director R&D VSSC in May 2025. Coming to the major achievements of Dr. Asraff, he has over 99 papers, nearly 100 papers presented or published at international and national conferences and journals. He created over 29 ME theses, and he has copyright for 5 softwares. And his PhD thesis was awarded the best Professor Prem Prakash best PhD thesis of 2017, instituted by the Indian Institute of Metals Trivandrum chapter. He has reviewed and approved the structural aspects of several launch vehicle structures for PSLV, P59, P60, and P61 flown missions, GSLV, that is H15 and LVM3. Coming to awards, he has won 5 Best Paper Awards for papers presented at various conferences, and he has won the ISRO Team Excellence Award in 2009 and the Astronautical Society of India's ASI Award for Rockets and Related Technologies for 2024. And academic activities, he has contributed a chapter for the book Introduction to Finite Element Analysis using C software, and he is the advisory member for many departments of various engineering colleges, and also a reviewer for international journals like Elsevier. And now over to you, Dr. Asraff sir, for his talk in the 2020 series.
Thank you, Jayakumar, for the nice introduction, and good evening to all. It's nice to see many of the persons who have been our seniors. And shall I start with the presentation? I'll stop the video and then I'll go ahead with my sharing of the presentation. Okay, Jayakumar?
Yes, sir. Okay, sir. Please go ahead.
I hope my screen is visible. My screen is visible? Hello?
No, sir.
No, sir. Screen is not visible.
You can share the full screen, sir. Like,
yeah, entire screen share. Is it visible now?
Yeah, visible.
Yes, sir. Full screen mode. Yes, sir.
So is this visible now, everybody?
Yes, yes.
Yes, yes.
Okay. Okay. So again, good evening to all. I'm going to talk about the most astonishing number in the world. This is why is this astonishing? Let us see. The most astonishing. This is called phi, and it was discovered in the 5th century BC by Pythagoreans, and it is called the golden ratio. And its value is 1.618, etc., etc. And it is denoted by the Greek letter phi, and it is called the most irrational number. And it has got various thinkers of various disciplines like engineering, mathematics, science, philosophy, music. Everybody have worked on this and contributed to this, and it has got many other names like divine proportion, divine section, golden number, section, mean, proportion, cut, etc., etc. Now let us see number system. We have got the number system. We have got real numbers. We have got complex numbers. Complex numbers, we all know it is denoted by x equal to a plus ib, where a is equal to root of -1. Whereas real numbers, we have got several numbers under the real numbers. So we have got the rational numbers, which can be expressed as a by b, where a and b are integers. We have got irrational numbers, which cannot be expressed by the a by b ratio. We have got integers. We have got whole numbers. We have got natural numbers also. So natural numbers is a subset of whole number, which is a subset of integer, which is a subset of rational numbers, which is a subset of real numbers. Whereas for irrational numbers, we have got several examples, like pi is an irrational number, phi is also an irrational number, e is also an irrational number. So phi is considered the most irrational number in the world. And an irrational number cannot be expressed as a fraction, as I told, a by b, and it is the decimal places are never ending and never repeating. So this, why is this so astonishing? Let us explore. I have put here various photographs of various walks of life, like we have put a heart here, then beautiful faces, then pyramids, then rabbits, so on and so forth. So let us explain. Let us see in various walks of our life how this beautiful number manifests itself. So what is the golden ratio? Golden ratio, by definition, if you have a line like this, and if you divide this line into two parts, let us say a and b, so the whole number is the whole line is actually a plus b. Now if you have this a plus b divided by a equal to a by b, for example, I have put it here, a plus b by a is equal to a by b. That ratio of this a by b ratio is called phi, or the golden ratio. Now you can get this an equation for this by solving this this equation by putting a equal to 5 and b equal to 1. So then a by b will be equal to 5 by 1 equal to 5, and then we'll have instead of a, we'll put 5 and then plus 1 divided by 5 equal to 5 divided by 1. This by cross multiplying, you will get a beautiful quadratic equation like this, which can be solved by the famous minus b square plus or minus root of 4ac square minus 4ac divided by 2a, and that comes to 1 plus or minus root 5 by 2. So here actually instead of plus, it has plus or minus, but however, when you put the minus, it will become negative. So I have not used the number, I have used the positive number only, which is called 1.618. So this is a never-ending number. Though this is called a ratio, it is again a non-ending number, and it is the most irrational number. Now let us see the manifestation of this golden ratio in mathematics. There are certain very interesting properties of golden ratio. For example, 1.618 square will be 2.618, and 1 divided by 1.618 will be 0.618, and 5 you can get by having taking square of 1 plus root of 1 plus 1 plus etc etc. And similarly, you can also get phi is equal to 1 plus 1 by 1 plus 1 by 1 plus and all that. You will again get the same number. And similarly, there is another strange equation. It is phi raised to n will be equal to phi raised to n minus 1 plus phi raised to n minus 2. Now let us see how to get this golden number in your calculator. Take 1 in a calculator, add 1, take reciprocal, add 1, take reciprocal, add 1, and all that. Continue this 9 times, you will reach golden ratio. Similarly, if you want to get it in other way, using square roots, you take 1 in your calculator, add 1, take square root, add 1, take square root, and continuously do this 9 times, you will get this golden ratio again. Now, I will also tell something about Fibonacci series. As you all know, Fibonacci series starts with 0, 1, 1, and so you have to add the consecutive numbers to the next number. For example, 1 plus 1 will be 2, 2 plus 1 will be 3, 3 plus 2 will be 5, 5 plus 8 will be 5 plus 3 will be 8, and so on and so forth. So this was discovered by Leonardo of Pisa. He is also called Fibonacci, and this is a statue of this person. And if you see, the strangest thing is that if you take any consecutive numbers and you divide the whole bigger number by the smaller number, you will get the golden ratio. For example, initially this ratio of its adjacent terms will be 1. As you know, this 1 by 1, I have not taken 0. 1 by 1 will be 1, and subsequently it is 2 by 1 will be 2. Subsequently, after this initial start transient, it starts stabilizing at this 1.620. For example, from 13 onwards, the 13th term onwards, it was starting stabilizing at this exactly at this number 1.618. So Fibonacci series in essence represents golden ratio. Now let us see in geometry, for example, in triangles, rectangles, circles, and spirals, how this golden ratio manifests itself. Now this is a rectangle which is divided, which is taken in the proportion 1.618 to 1. Now if you take out the square portion of this rectangle, I construct a square portion of this rectangle, then what is remaining is going to be another golden rectangle. And if you take out this square out of this, then I'll again get a golden rectangle and so forth. This continues infinitely. And similarly, if you take, this is called a golden triangle, and this golden triangle is actually having 70 to 72 and 36 degree as its angle included angles. Now, if you construct an angle bisector at B, it will touch this point, and this distance AD divided by DC will be 1.618, and again you will get a golden triangle. And if you have angle bisector of this, again you will get a golden triangle, and if you continue like this, you will get golden triangles one after the other. Now you can also have divide the circle in this ratio, that is 1.618, and this angle 137.5, which is coming in the denominator, is actually the called golden angle, and this ratio is the golden ratio. Now, similarly, there is another interesting property for this golden rectangle. You have the golden rectangle like this, and you have the main diagonal of this golden rectangle, biggest rectangle, and I take out the square as I said earlier, then you get another golden rectangle and have one more diagonal. Now subsequently all the other smaller rectangles and all that will have the same diagonal. If you see this, it has got this diagonal, and if you take this, it has got this diagonal. If you take this square, this rectangle, it has got this diagonal. This rectangle has got this, and so on and so forth. It's a very interesting answer. It converges to one point. All these rectangles converge to this point. Similarly, there is another thing called golden logarithmic spiral. This is also called a growth spiral or equiangular spiral or golden spiral or spira mirabilis. It is given by the ratio r is equal to a into e raised to b theta, where a and b are, r is the radius, theta is the angle, and e of course is the exponent, and a and b are constants. And the strangest property of that is that the angle between any radial line from a point, if you draw from any point, you draw a radial line, and to the tangent at that point, the angle will be constant at any point you take. So this golden spiral, logarithmic spiral is also, and I'll come to this a bit later. And you can have an inscribe a golden spiral, or rather rectangle, golden rectangle inside a spiral, and you can see how it manifests itself. So it goes all along the golden rectangle. Also, the golden spiral and golden rectangle are almost similar. Now let us come to a pentagram. A pentagram is actually a 5-pointed star, as seen here, which normally we in our school days in childhood we used to draw without lifting your pen from the paper. It's a 5-pointed star, and it has got a very strange property that all these lengths are in golden ratio. For example, A divided by B is actually golden ratio, and B divided by C is golden ratio, and C divided by D is also golden ratio. So this pentagram is actually a manifestation of a golden ratio. And another strange thing is that you can have a pentagon inside a pentagon. You can see the internal point is called a pentagon, and if you draw lines, diagonals like this, it will again become a pentagon. So this pentagram inside a pentagon, and you can go on and on like that. Now we can see golden ratio in art also. For example, Leonardo da Vinci, who lived in the 16th century. He had drawn two very famous paintings called Madonna of the Rocks, and there are two versions of the same painting. One is in the Paris Museum, Louvre Museum, and another is the London version. And both these paintings are of this proportion 1.6. Similarly, Da Vinci also has painted one more a very beautiful painting called Leda and the Swan, and the hairdo of this lady is actually in the golden logarithmic spiral. And he has also painted another thing called Deluge, which is again plenty of you can see plenty of logarithmic spiral in this. Similarly, world famous Spanish surrealistic artist Salvador Dali is no more. He is a surrealistic artist. So in his painting, this famous painting, actually this is having the ratio of 1.6 again, the aspect ratio, and he has given the sacrament, Last Supper. And you can see there are two important things in this. The painting is according to the gold ratio, first thing. Second thing is dodecahedron is drawn engulfing the table. So this is a dodecahedron. If you see, go by the dodecahedron's definition, you will also see it is basically made of this golden ratio again. Now let us see golden ratio in architecture. This is a very famous temple of goddess Athena in Greece, in dilapidated condition. Now it is refurbished. If you see the facade from the elevation of this, it is perfectly as per this 1.618 ratio. And if you see the pyramids of Egypt, this is the pyramid of Khufu, Great Pyramid of Khufu in Giza. And you can see, if you take the slant height, yes, to the base half of base width, it is almost square, and we take this angle of S by A, it is again according to this golden ratio. And now coming to the tiling patterns, actually, as I told you earlier, we have got this. This is actually a pentagon, and inside this a pentagon, you can have a pentagram, and then there are you can have many number of geometric shapes. All these geometric shapes can be drawn as per the golden ratio. For example, this is 5 and this is 1. For example, if you take this gray area, it becomes 5 here, 1 here, 1 here, and all that. So you can have many number of golden ratio patterns in this, and this was invented by Professor Roger Penrose at Oxford University. And you can have tilings, and the tilings are generally seen in places of worship. And you can see Roger Penrose of Oxford University is a Nobel laureate in physics, and you can see he's himself standing over this tilings. And there is another thing called Dubai frame. People who have visited the Gulf can see this. It is actually a frame, a freestanding frame, separating the old and new Dubai. And if you can see the outer dimensions of it, 150 meters by 93 meters, it is actually as per the golden ratio again. Now let us see golden ratio in nature. In nature, it is told that hurricanes generally are of this nature, of logarithmic spiral. And logarithmic spiral, as I told you earlier, it has got this golden ratio property, and it is a typical hurricane over Iceland. And if you see, this is a broccoli, it's a cauliflower. You can see that it consists of many buds. All these things are of golden spiral. For example, this is the global view of this cauliflower. It is called Roman cauliflower, and if you see, this is a global picture. And if you take a zoomed view of this, each one, you can see there are spirals in the logarithmic spiral inside that. But if you see zoom out and see, all these things are logarithmic spirals. If you zoom one, it is again a logarithmic spiral. If you further zoom, it is again logarithmic spiral, logarithmic spiral, logarithmic spiral. Fifth one, everywhere you can see logarithmic spiral, and everything is actually golden ratio. Now, if you can see this pineapple, a well-proportioned pineapple, I've seen myself. I should demonstrate it to many of my participants. It has got actually patterns like this. It has got these patterns. If you see this is actually one pattern like this, another pattern like this, another pattern like this. So you have 5 spirals here, generally 8 spirals here, and 13 spirals here. So these are Fibonacci numbers. As you can see, 5 plus 8 is actually 13. And if you take this ratio of 13 by 8, it should be 1 point or more 1.6. And similarly, 8 by 5 is also 1.6. So this is very clearly seen in pineapple. And for example, in pine cone, there are actually spirals. You can see there are clockwise spirals and anti-clockwise spirals as shown here. And generally, they will be in the golden ratio or Fibonacci numbers 13 and 8. And the Fibonacci series is actually nothing but golden number. And the golden ratio in sunflower, this I have myself seen at Munnar. And actually, if you see the seeds, the central portion of this, you can see the seeds of this sunflower, and you can see these are arranged in patterns. For example, there are clockwise spirals, and there are anti-clockwise spirals as well. If you see here, the number of spirals in this clockwise direction is 34, whereas the other one will be 55. So this is again the golden ratio number or Fibonacci numbers. If you take the ratio of 55 by 34, it will be Fibonacci, or rather it will be golden number. And then in plants also, I've seen this. That is, if you take the stem and there are leaves arranged here, the first leaf, actually the first leaf and second leaf, it will be turning by this angle 137.5, which I have shown earlier, which is nothing but the golden ratio number. And if you take this leaf T 2 to 3, again it will go and clockwise by this amount 137.5, and it will get lifted up also. Similarly, 3 to 4, 4 to 5, and all that. It is told that by having a pattern like this, plants get a good sunlight during its development, which is very essential for it, for the photosynthesis and all that. So this is actually a plant. This I've taken. This video was taken by me at Munnar, as I told you earlier. This is actually sunflower plant. In this plant also, I've seen the leaves are arranged in this ratio of 137.5. One leaf will turn clockwise, then the next leaf will be at this angle. I'm not saying that every leaf is that way, but there are exceptions as well. But in general, I've seen that its pattern is as per 137.5 degrees. Now, if you see the acacia tree leaves, which are very common in our part of the country, again here also the leaves are arranged in this particular fashion of 137.5 clockwise, and it will be lifted up like that. And if you see certain flowers, for example, in dahlia, you are told that the angle between petals, successive petals, are also of this ratio. For example, petal number 1, 2, 3, and it goes like this clockwise, and it has got this golden angle 137.5. Now there is actually something called bifurcation angle. If you see the leaves, actually the veins from the main vein, it actually has bifurcates. This bifurcation angle is actually 34.5, which is nothing but a golden ratio number. So this is called the modeling golden sections in plants. This is a very important science. It's called phi tau axis, and many people work on this, and there are several publications also. And you see this bifurcation angle is seen in cypress leaves also. For example, this angle is 34.4. As I told you, 35.4 is nothing but this golden ratio. This 1.618 is 1 by 0.618. So 1 minus 1 by 0.618 to 90 is 34.4, and this is the angle which I have told. Similarly, in bamboo branches also, you can see the same angle of 34.4, and similarly in the poplar trees also, this same angle of 35.4 is seen. Similarly, in a peach tree, you get a different angle, 90 into 0.618, which is 55.6. This is also another golden ratio angle and seen in peach trees. Now let us explore animal world. Animal world, you have the mollusk, you have nautilus. This nautilus is actually seen at, I could see that at Kanyakumari. If you take a cross section of this nautilus, it is actually a shell of a mollusk, and you can see these chambers are all in the golden ratio. For example, this is perfectly according to the logarithmic spiral. And if you see the breeding of rabbits, if you it is told that if you put a pair of rabbits in a container, in a closed container, and allow it to breed, after the first month it will become mature, the next month mature, and then it will give birth to another one, and the old thing will remain. So here old things will remain, old pair, and this will give birth to another pair, and after the next month this will give to another pair, and this will give to this will remain as such, and first after the next month it will give another pair. Like that it multiplies, and I've put it in a color code. For example, black are the original ones, and the first couple, first batch, first team, first pair to come out, it's a red one, subsequently blue, subsequently a smaller black and green, and so on. So these are all, if you take the number of pairs, all these numbers, all these pairs are actually perfectly as per the Fibonacci series, and Fibonacci series is nothing but golden ratio. Now let us see the family tree of honeybees in a beehive. It is told that a honeybee will consist of queens and males and female bees. And males have got females have got two parents, a father and a mother, whereas a male bee will have only one parent. So if you see the total number of bees in a beehive, there will be a bee, a male bee and female bee. A female bee will have two parents, whereas a male bee will have only one parent, and this female bee will have two parents, and so on and so forth. So here these are the grandparents, great grandparents, and great great grandparents. So if you see the number, it will be 5, this will be 3, this will be 2, this will be 1, 1. All these things are Fibonacci numbers, and if you further go up, you will have more and more of Fibonacci series numbers as the number of females and males. And this is the complete family tree, as I have told you earlier, for a male bee, and you can see all these are the total number of bees, and you can see this is as per golden ratio. And another important interesting thing is that number of males is also golden as per Fibonacci series. Number of females also as per Fibonacci series, and total is also as per Fibonacci series. So if you take any honeybee beehive, the number of males, bees, female bees, everything will be as per golden ratio. And if you see the peregrine falcon, this is actually a very famous falcon which has got very high speeds. The flight path of the peregrine falcon, it is reported that it is as per a logarithmic spiral or equiangular spiral. It is the beauty is that this has got a same angle with the spender. So if there is a fish here in a pond, and this will start look through the sides only. This has got eyes on the sides. So this it will continuously view this prey, and it will continuously take a turn like this. It cannot go like this because its eyes are located on either side. So it takes a turn like this and goes and catches the prey, and every time it subtends the same angle so that it can see the prey all throughout the flight path. Now this is reported curved flight paths and sideways vision in peregrine falcons. This has been reported in literature also. And let us see if a golden ratio in human body, a perfectly shaped human body, perfectly proportioned human body is supposed to be according to this golden ratio. For example, you have the navel height from the head, tip of the head, it will be 38 to 60. This is actually golden ratio. It is also told that all the hands, arms, everything is as per golden ratio. For example, it is approximately like this. And another interesting fact is that the golden ratio is seen in blood pressure also, in sleeping pressure. So nighttime blood pressure, generally we have got this 120/80 as the conventional systolic to diastolic ratio. But when you take a rest, during night time, the average systolic pressure to the diastolic pressure is actually according to its golden ratio. It is also reported in literature. And let us see the golden ratio in universe. And some of the galaxies are supposedly logarithmic galaxies, for example, Milky Way, Pinwheel galaxy, all are according to the spiral golden ratio, golden spirals. And let us see the golden ratio in structural engineering, which is very interesting. You have seen many domes. We have got domes. Generally, they are used in places of worship. And let us see a spherical shell. A spherical shell under self-weight is governed by the Hooke's stress is governed by this equation, which boils down to this theta is equal to 51.5 degrees. That is, for this up to here, it will be compression, then it will be tension. So if you have a dome like this up to here, then there will not be any compression. And earlier people used to use only brick materials and brittle materials like stones and all that. So there's no tension permitted. So they used to define, or they used to construct the dome up to here only golden ratio angle. Subsequently, if you do here, it will have tension, vertical cracks due to tension. So you need to have reinforced concrete. So this I analyzed in using ANSYS finite element program, and this was my own work in which I modeled a simple dome with the internal self weight, and then plotted the Hooke's stress, and I have found that beyond this golden ratio angle of 51.5 degrees, tension is there on the red zone, and only compression is there only on the cyan portion. So if you have a dome defined like this, it can survive in brittle materials, but if you extend it, then you need to have either reinforcement or ductile materials. Now let us see golden ratio is a measure of beauty. It is widely told that an oval face is the most beautiful face, and the most important angle. You have seen several dimensions are measured here, but one striking thing which I want to tell you is this tip. This is actually the distance 3. That is the tip of the forehead to the lips, and from the lips to the chin. If this, sorry, okay, this angle nose, this angle, the 3 to 5. This is actually 3, and this is actually 5. This is tip to the nose tip. This can be considered as 5, and this is, let us say, nose to the chin. If this is actually as per golden ratio, then almost the face is supposedly most attractive, most beautiful face. So all these ratios are given here, 3 to 5. I've seen that 3 to 5 is very important, and vertical tip to nose. So if this ratio is satisfied, then then many people have attributed that face to as the most important or most beautiful face. Now let us see the smile design. Generally, dentists use this for defining this smile design, for defining teeth. And you can see this in this elevation view. It will be 1.62 to 1 to 1.62, and all that. All these things are generally shaped or kept as per golden ratio. And this 1.6, this ratio of this width to this width will be as per golden ratio, and this width to this width will be as per golden ratio. And this is also reported. And I had several times rounds of interactions with the dentists, which they also confirm that they do the smile design of the teeth using the golden ratio principle. Now let us see in everyday life, where is the golden ratio. For example, all the credit cards, debit cards which we use are all according to this golden ratio, and legal paper size also according to this golden ratio. Even the National Geographic emblem is also as per golden ratio, and all business cards all are as per this ratio. Now to conclude, I have taken 25 minutes. Golden ratio is called the lesser known cousin of the famous mathematical constant pi, and new research reveals more and more manifestations of this great number in the various walks of our life. And this number basically denotes beauty and perfection, and this number could be a signature of Almighty. So with that, I finish. These are the references. I have studied Dranbaum book, and with a very nice book, very good book, in which I have drawn my inspiration from that book only. Subsequently, I referred to Maria Levy also. And thank you, friends. Thank you all. And I'd be happy to answer questions if any.
Thank you very much, sir. We had a very interesting talk. It was an excellent talk on a very interesting topic. on the golden ratio, different manifestations. Speaker has presented the different manifestations, that is in nature, in geometry, in paintings, in architecture, in plants, animals, and in everyday life. So this really leaves us with more questions than answers. That is, what is this number, or how it is, what is the basis that everywhere we are getting this number? So as Sir has concluded, it may be the signature of Almighty, which we are yet to explore. We can take a couple of questions from the participants. The participants can unmute and ask a couple of questions, and with a couple of questions, we can conclude due to paucity of time. Participants may please unmute and ask.
Hello.
Yeah,
Yeah,
good
yes,
evening,
sir.
sir. I'm audible.
Yeah.
Sir, actually, I'm Baby Sebastian. It was a very nice talk, very interesting. And that number, okay, we hear about the number long, okay, many occasions, okay, but now only we got the beauty of the number also. So actually, you put all the plant and all, it is mainly for getting sunrise as well as many requirements are there. But human
Correct.
being, you told the
Yeah.
beauty, what may be the reason for such a figure? Is it due to beauty, or is it due to some other physical stability, or is it due to some other requirement?
Basically, I feel it is because of beauty. See, there was an experiment conducted with various rectangles. Many people were distributed rectangles and asked which one is the most beautiful rectangle or most proportioned rectangle. And it seems many people have selected the rectangle. Rectangle means a box kind of thing with golden ratio properties. So this had been done using as an exercise in psychology, sorry, not psychology. Many people have mentioned that this. So you can see most of the windows are also according to this golden ratio. Most of the house plots, if you can see, generally house plots, people prefer this rectangular shape. And if you see, if it is as per proportion, as per golden rectangle, golden ratio, it will have maximum utility as well. For example, if you have a square plot for a house plot construction, that is a worst kind of a plot, because you cannot construct anything. You will have the central house only. But if you have a rectangle, golden rectangle, then centrally you can have the house, and front side you have got a lot of area for car parking and a garden. Back side you can have a kitchen garden as well. So it appears that from a beauty point of view, from a convenience point of view, this is being used. And I was told by some private company people that their products are also designed as per mechanical products. Machine products are also machine parts are also designed as per this ratio. This is kind of a ഇത് മലയാളത്തിൽ പറയും ലക്ഷണമൊത്തത്. So the ലക്ഷണമൊത്തത് has got only a ratio. You cannot exactly, for example, you have നമ്മുടെ കുത്തുവിളക്ക് എന്ന് പറയും, നമ്മുടെ നിലവിളക്ക് has got the traditional lamp which we use for lighting in functions, and this traditional lamp has got a particular ratio of the ratio of the height to the plate where the oil is put, and then you have the wheels. So all these things should be proportioned as per a particular ratio. So my point is, everything should be as per according to a ratio. So this ratio is having some psychological effect inside. So most people prefer everything in a proportion, a special way. So probably this could be the answer for that. It's
Okay,
more
sir,
of
thank you.
psychology.
Okay. Yes.
Yeah, good evening, sir. Yegumat here. Just one question, sir.
Yeah.
So it was a very interesting talk. You mentioned that this has the Great Pyramid, Great Pyramid, as well as the Athena temple. These were made after
Yeah.
the golden ratio. So if you see, this dates back to almost 3,000 years or 2,000 years, like that. So
Yeah, from
known
antiquity,
that
from BC also.
BC onwards it is known. So was it known
Yeah.
like that, even though not known by the name golden ratios, was it known to them, or it just happened that it has to be of this ratio so that it looks attractive?
Yeah, correct. Visually, it is appealing to have this ratio. So that could be one of the reasons. So those people, they were basically looking at basically visual appeal. That is one aspect. Second aspect, whether it has got some other internal meaning for this pyramid. Pyramid actually has got a lot of mysteries. hid inside, because it is used for it's used as a burial place for the kings. So I do not know whether they have got some other spiritual meaning for this particular ratio, but visually it is really appealing.
Okay, okay.
So due to paucity of time, we are
Yeah.
not in a position to take more questions. If there are more
Yeah.
questions, it may be directly posted to Asraff sir so that he can answer. So it was a very interesting talk on behalf of all the participants who has listened, and on behalf of SSA Trivandrum chapter, we thank you for giving this interesting talk, sir. Thank you. Thank you very much.
Thank you.
Thank you.
Shall I
Asraff.
exit now?
It's really
Yeah,
a very nice talk.
Welcome, Soumya.
It's
Thank you
quite
for coming.
interesting to observe nature's ratio aspect.
Thank you, Jayanti. Thank you.
Thank you, sir.
Very good lecture.